Now let us introduce our next problem, which will be a typical problem on ladder. So this is problem number 2 for us, and it says a uniform ladder of length 5 meters and mass 16 kg rests on a rough horizontal floor and leans against a smooth vertical wall. The angle made by the ladder with the horizontal is 36.9 degree. The coefficient of static friction between the floor and the ladder is 0.700. How far up the ladder can an 80 kg man climb before it slips? So you can understand by reading the question, sometime during the problem we have to introduce the force of limiting friction acting on this ladder plus man system. So here is this construction of the figure, a vertical smooth wall and a horizontal rough floor, and suppose the ladder is placed on this rough floor leaning against the wall as I am showing in my figure. So I'll name this ladder as AB, A being the foot and B being the topmost point of the ladder, and since it's uniform, its center of mass must coincide with the midpoint of the ladder, that is the point C in my figure. Let us take down the data here. They are telling the length of the ladder is capital L is equal to 5.00 meter. Therefore, if I could show in my figure as well, the length AB is L, which is 5 meter. And they have also said the mass of the ladder, that is capital M, is equal to 16.0 kg, and the angle made by the ladder with the horizontal, this is this angle theta. This theta is given to be 36.9 degree. A special value of the angle is convenient. Sine 36.9 degrees 3 by 5, while cos 36.9 degrees 4 by 5. Useful results. The coefficients of static friction between the floor and the ladder is 0.700. So here you understand that where the ladder has touched this rough horizontal floor, the frictional coefficient mu s, this mu s value is 0.700. We shall need it while finding the force of limiting friction acting on the ladder. How far up the ladder can a man of mass 80 kg climb before it slips? So let me show here an arbitrary position of the man up the ladder. This is shown by this red dot. This red dot represents this man. And suppose at any given time, the man has climbed up to a distance of x, measured along the length starting from the foot A of the ladder. So this is, the distance is taken to be x, a variable quantity because the man keeps on climbing, and at a certain point, the whole ladder plus man system begins to slip. So with this understanding, we have taken down all the data here. Well, the mass of the man taken to be small m, that is also given to be 80 kg. We have to find out that how far up the ladder can this 80 kg man climb before the system begins to slip. That is the value of x at which the system just begins to slip. So in a general situation, without any reference to the slipping condition, let us identify the forces acting on this ladder plus man system. Here is the force of gravity acting on the ladder vertically downwards to the midpoint, that is C. So this is the gravity force, and that is capital M into G. I have taken the ladder's mass to be capital M in my symbols. And similarly, the force of gravity acting on the man, and that is also acting vertically downwards, that is small m into G. Since the wall is smooth, the contact force exerted on the ladder at point B is a normal force only acting to the left in my figure, and that force I am calling it N dash, as I have done in my theoretical part of this class. And what about the contact force given by the floor? Since the floor is rough and the ladder tends to slip always to the left in this situation, with or without the man, the frictional component of the contact force acts horizontally to the right. This is a static frictional force, and I shall call it Fs, because before the slipping begins, the foot of the ladder A has got no relative motion with respect to the floor, hence the frictional force is Fs acting to the right to stop any possible slip to the left in my figure. And the normal component of the contact force given by the floor is of course acting vertically upwards. I shall call this force as N as usual. So here are the forces acting on this ladder plus man system, the gravity forces, the contact force given by the wall, and the contact force components given by the rough floor. So as before, considering this general situation, let us write down the conditions for translational and rotational equilibrium for the ladder plus man system. We make our choice of a coordinate system that you can see we take direction to the right to be positive x direction and direction upward to be plus y direction. And similarly, while writing the torque equation, we shall consider a counterclockwise sense of rotation to be the positive direction, that's plus. And for translational equilibrium of this ladder plus man system, there are two equations for x motion and y motion. Taking the forces in the x direction, this is sigma fx, as you can see, is coming out to be Fs acting to the right, and the normal force given by the wall, that is N dash acting to the left, Fs minus N dash must be equal to 0. Therefore, we can write that the frictional force at the ground and the normal force by the wall, they have the same magnitude. That is equation number 1 for us. Similarly, writing the condition of translational equilibrium in the y direction, sigma Fy also is 0. And what are those forces? An upward normal force given by the floor, and I have got two gravity forces, one acting on the ladder, mg, capital M into g, and one acting on this man, that is small m into g, and therefore I have got n minus mg minus small m into g. This again should be equal to 0, which gives that the normal force is coming out to be capital M plus small m inside bracket into the acceleration due to gravity small g. That is my equation number 2. We have got here two equations for the frictional force of the ground and the normal force given by the ground. Let us now go for writing down the torque equation for rotational equilibrium of this ladder plus man system. And my choice will be the point A through which there are two forces acting and hence their torques are 0. So I could write down for rotational equilibrium the net torque taken about the point A, that is sigma tau A. Let's start writing. But before that, we have already seen these two forces N and Fs. Since they pass through the point A, they have 0 torque about the point A, and you don't need to consider them. But before I write down the torques of the other forces, these two gravity forces and the force N dash at the wall, let us show here in the figure the length of the momentums of these forces. So to do this, once again, I extend the line of action of the force mg here, and also the line of action for the force small m into g acting on the man here. And you understand from the figure that since, let me show it here, since this angle is theta and the length of the ladder is capital L, the length AC is L by 2, is not it, C is the midpoint. So AC is L by 2, and this angle being theta, this length is coming out to be L by 2 cos theta, which is the momentum of the force capital M into G taken about this point A. And similarly, if we look at this, the man is taken at a distance of x measured along the length of the ladder from the point A, and therefore this length being x, I can just give it some name. Let me call this point as the point D.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.